For the first example, I chose a pretty simple problem. Um, it's this particular problem is really easy. It's just to get you guys into the gist of how we're going to do things in this module. All right. So what I like to do before I start anything is I like to label this reaction right here as my king reaction. All right. So the problem is actually asking us for calculate delta H for this reaction, and it says acetylene, that's C2H4, plus hydrogen gas makes ethane, C2H6, from the following data. All right. And so yeah, I like to label this reaction up here our king reaction, and you'll see why right now. Okay, so these three reactions right here, I'm going to call them sub-reactions, so let's go to name them, or actually label them. Okay, so it's going to be reaction 1, this is reaction 2, and this is reaction 3. Alright, so basically what we're doing is we're trying to get reactions 1, 2, and 3, and we're going to rearrange them such that they look like the king reaction once you jumble all of them up together. Alright, so let's go and get to it. So the first step to start off with actually is just start off with one of your reactants. All right. So one of the reactants in our king reaction is C2H4, known as acetylene. You don't have to know that. It's yeah, don't know it. So we look at acetylene and we look at our three reactions down here, and we have to find out in which one of these three reactions do we find acetylene. Alright, and actually the only place where we find C2H4 is right here in our first reaction, right? Because if you see, if you look at the other reactions, it's not in there. And what we're trying to do is we're trying to get this C2H4 to be on the same side as this C2H4, and if you notice, they're both reactants, right? So this is the reactant, this is the reactant. Okay, so that's good. And they also both have a coefficient of 1, right? They both have an imaginary 1, so we don't have to change the coefficient of either one of these. Alright? So let's go ahead and start off, let's go ahead and continue with the next one. Alright, so let's look at hydrogen gas now. Alright, H2. If we look at our reactions, the only other place that we can find H2 is in our third reaction right here. Right? And if you notice, they're both reactants. They're both coefficient of 1. So we don't have to really do anything with this one either. So this is a reactant. This is a reactant. They're both coefficients of 1. They're both reactants. They're both in the same state. Right? So it's fine just the way it is. Okay. So now let's look at our last reagent in our king reaction. And it's actually a product, sorry. But it's ethane. Alright, so let's go and look for where we find C2H6. And if you notice, it's in the second reaction, or reaction number 2. And let's see, there's one thing that's very wrong with this, as just the way it is right now. It's that in our king reaction, C2H6 is a product, while over here it's a reactant, which is no good, right? Because we're trying to get these three reactions to mimic the king reaction. So we're going to have to flip this entire reaction around such that this C2H6 is a product, just like how C2H6 is a product in the king reaction. Alright, so it's going to make it a little simple right here. I'm just going to use these backward and forward arrows. So right now we're going to rewrite this equation, or this reaction, and we're going to completely flip it around. And a very important thing to do when you flip a reaction around is to also change the sign of its delta H. Right? So this right here, we're going to multiply it by -1, which will make it a positive 1,560 kilojoules per mole. Right? So let me go ahead and rewrite these reactions. Remember, the first and third reaction, we did not change anything about them. So reaction 1 is going to be C2H4 gas plus 3 O2 gas, and it's going to form 2 carbon dioxide gas and 2 waters. And guys, it's a good habit to start off. It's not very necessary for this problem in particular, but it's very important that you guys label your the states of the stuff in these reactions. All right, because sometimes you might find in this case we have liquid water. In some cases we might find gaseous water, and gaseous water and liquid water are not the same. All right, so you'll see why we want things to be the same in a moment. All right, so equation 2. Remember that we flipped equation 2. So let's go and draw the 2 carbon dioxides first. 2 carbon dioxide gas plus 3 waters liquid. And that's going to react to form 7 halves of O2 gas plus just 1 C2H6 gas. Alright, and delta H, remember we're changing the sign of this, so this is going to be positive 1,560 kilojoules per mole. Now reaction 3, remember we did not do anything to this one either, so let's go to just write H2 gas plus 1/2 O2 gas, and that's going to react to form H2O liquid. Right? And let's go and just bring down the delta H, which is negative 285.8 kilojoules per mole. Right? So now that we've rearranged our equations, let's go in and see what cancels out. And if you guys remember, like similar to what we did when we were working on the aqueous reactions, where we canceled out things inside the ionic equation to give ourselves a net ionic equation. So it's very similar to that. We're just going to look for things that cancel out. All right. So, for example, right here, right off the bat, I can see that we have two gaseous carbon dioxides on the reactant side, and 2 carbon dioxides gaseous on the product side. All right. So reactant cancel out product. So those cancel out. All right. We have 2 and 2. Okay. So let's see what else cancels out. Okay, so for those of you who might not be that proficient in math, we have three oxygens is the same thing as 6 halves, right? I hope everyone can see that. So 6 halves plus the 1/2 down here is going to give us 7.5 total, right? Or 7 halves total, which cancels out with this 7 halves over here. So this cancels out with this, and okay, so we get rid of that from our reactions. Okay, we have 3 waters over here, as well as 1 water over here, and 2 waters over here. So a total of 3 waters on the product side, and the 3 waters that we cancel out over here on the reactants. Okay, so those perfectly cancel out as well. Let me go ahead and erase this just so it doesn't confuse you guys. I do not see anything else that cancels out. All right. So now let's write what we're left with. I'll just keep on writing in purple. Alright, so this is kind of like the sum right here. Okay, so let's just let's write all the stuff that's left over. Alright, so we have, sorry. That was C2H4, right? Yeah. C2H4, gas, plus H2 gas. And that's going to form C2H6 gas. And just in case you didn't notice, this that we ended up with down here is the exact same thing as our King reaction, which is what we want. Alright? That tells us that we did this equation, or this all this rearranging and all this mumbo jumbo in here that we did. We know we did it right because we ended up with the King reaction. Alright? So actually the next step, we're not done yet. The next step is to add up these delta H's, and that'll give us our answer. Alright, so we have negative 1041, or 1411, plus 1560, minus 285.8. And that actually gives me a grand total of negative 136.8 kilojoules per mole. Alright? And this is actually going to be our answer. So we did all of that over there, and it was all just to get this negative 136.8 kilojoules per mole. Alright? So let's go ahead and get to a little bit of a harder problem. Something you're more likely to see on exam. Okay, so let's start off by numbering our reactions just like we did before. So we're going to call this reaction 1, reaction 2, and reaction 3. So let's go ahead and do the same thing that we did on the other reaction. Let's just go ahead and start off with the first reactant, which is 4 ammonias. Alright, so in our reactions we see that we have 2 ammonias over here. But are 2 ammonias and 4 ammonias the same? No, so we're going to have to multiply this entire equation by 2. Alright, so we're multiplying all this by 2 so that we can make this 2 a 4 in order to have the same amount of ammonias. Alright, but another thing that's different between this ammonia and the King reaction ammonia is that this ammonia is a product and this one over here is a reactant. So we're going to multiply by 2 and flip it around. Alright, so let's go ahead and make note of that. Okay, so let's continue with the next reactant over here, which is 5 oxygen gases. And we notice that there is oxygen gas in 2 places in our reactions. Alright, and I'm sure all of you know that there's several ways to add up to get 5. So this right here can be 3, this one can be 2, this one can be 4, and this one could be 1. You know, there's several ways to do this. We don't quite know yet. So I don't want to multiply by certain numbers yet because it might throw off other things in our King reaction. Alright, so we're going to skip that one for now, and I'll show you guys, I'll point out to you guys right now how how these products over here can actually solve our problem with oxygen. Alright, so let's just go ahead and skip that one for now. Okay, so we have 4 NOs, right? NO gas. And we see that we have NO over here as well. Alright, this is the only place that we find NO. And these are both products, which is good. Right? But the only thing that's different is that this NO in our King reaction has 4, while over here we have only 2. Right? So we're going to go ahead and multiply this nitrogen monoxide by 2 in order to make this 2 a 4, just like we see in our King reaction. Alright? So let's go to leave that one alone, and let me get a different color. Not that one. We're going to go ahead and continue with our water right here. Okay, so we have 6 waters, 6 H2Os, and they're gaseous form, right? And we're going to go ahead and look at our reactions, and we see that we find 2 waters over here, right? And 2 is not the same as 6, so as you can probably guess by now, we're going to go to multiply this reaction by 3. In order to get the same amount of H2O, right? And they're both products, so we don't want to flip around the equations either. And so let's go ahead and start doing that. Let's rewrite our reactions. And an important thing I wanted to point out to you guys is, for example, right here in our first reaction, we're multiplying this entire reaction by 2, right? Which means we also have to multiply the delta H by 2. So over here we have to multiply, in the second reaction we have to multiply this delta H by 2 as well. And the last one we have to multiply by 3. And we also have to change the sign of the second one, right? Because we said that we're flipping it around as we see right here. Okay, so that's something very important to keep track of, because there's no point in doing all this stuff with these reactions, right, if you're going to mess up with the delta H's over here, because that's ultimately what the products, or what the answer is going to be to these problems if you see them on an exam. Alright, so it's going to rewrite equation 1, or reaction 1, which is N2 gas plus O2 gas. Alright, I'm sorry, remember that we're supposed to multiply this one by 2, so let's go do 2 N2 gas plus 2 O2 gas. And that's going to react to form 4 nitrogen monoxides. Right? And the delta H, let's go ahead and do that math right now. So negative 180.5 times 2 is 361. So we're going to go ahead and write negative 361 kilojoules. Right? So now reaction 2, and we see that we have we're multiplying this one by 2, so 2N2 gas. Or actually, I'm sorry, not only are we multiplying by 2, but we're also flipping it around, right? So let's go and start off by writing this those 4 ammonias right? So 4NH3 gas, and that's going to react to form. And I'm writing the reaction arrow all the way over here just so it makes it easier for us to visualize what's a reactant and what's a product when we get to canceling out stuff. So I know it looks a little bit weird with all that extra space, but just know that that's a purpose for doing that. Okay, so let's go ahead and start off by writing the 2N2 gases, and then 6 hydrogen gases. And the delta H for this reaction is actually going to be, change the sign, so positive 91.8 times 2, it gives me 183.6. So positive 183.6 kilojoules. Right? So now equation 3. Oh, and one thing I like to point out to you guys is, notice how I wrote the actual, I actually wrote out positive 183.6. And I like doing that just so you don't second guess yourself when you look at your reactions again. Like, you know how at the end we add them all up. I think it's just best to specify it is positive just so you don't second guess yourself and say, oh, was this negative? Was this positive? And you don't have to run into that confusion on an exam. All right, it might save you a couple moments of time, and might actually save you a headache as well and give you the correct answer. All right. So now let's go ahead and start off by writing equation 3. We're multiplying that one by 3, and we're not flipping it around. Okay, so let's go ahead and start off by writing 6H2 gas plus 3O2 gas is going to react to form 6H2Os, and those are going to be gas. All right, and delta H times 3, so we're going to go ahead and get that negative 483.6 times 3, so 483.6 times 3 gives us negative 1,450.8 kilojoules. Alright, so before we do any of the math, let's just make sure that all our work was correct. Alright, so let's see what cancels out here. We see that we have 2 nitrogen gases over here. That cancels out with these 2 nitrogen gases. Let's see here. 6 hydrogen gases cancel out 6 hydrogen gases. And I don't see anything else that cancels out. Right? So let's go ahead and write the sum of this down here. And we actually have 4 NH3s gas. Plus 3 plus 2 makes 5 oxygen gases. And that's going to react to form 4 nitrogen monoxide gases and 6 H2Os gas. Right? So just to make sure we did this correctly, let's compare this to our King reaction. And we notice that we have the exact same 4 ammonias right here. We have the exact same 5 oxygens, 4 nitrogen monoxides, and 6 H2O gases. Right? So we know that we did this correctly. Okay, so now let's add up our delta H's. So I'm going to go ahead and start off by writing out 183.6 minus 1450.8 minus 361. And that gives me a total of negative 1,628.2 kilojoules. Alright, and this is actually our final answer. Whoa, I kind of boxed it in ugly. And that's our final answer. I'll probably be uploading another video because in my Friday workshop I actually showed them some alternate method that one of my students last semester used. And some of you might find it easier. For those of you who are better at math, and you might find that other method easier. So go ahead and check it out if you want to see it. But a lot of people were confused about it. So if you like this method, then stick to this one because the other one might just confuse you. Alright, so let me know if you have any questions. Feel free to email me. And yeah, thanks for watching.